Hello, everyone. Good morning, good afternoon. My name is Carmen Guguta, and I'm your usual host from Technobis Crystallization Systems. Welcome to today's webinar, which is in the format of a training. I am here today with my colleague, Jyoti Yadav, our application specialist, that will present today nucleation kinetics from induction time measurements, how you can do that with the Crystal16. But just before you start, I would like to share with you a bit more information, technical, let's say, information about this training. Is being recorded and it will be made available to you tomorrow. You'll receive an email with a notification where you can actually re-watch the webinar in the coming days. The webinar will be available on our website as well, and also on our YouTube channel. If you have questions, please use the chat question function of this platform. I think at the end we can also unmute you and also share with us your questions. And let's see it at the end. It will last about 30 to 45 minutes, I think, including questions. If after this webinar training you have still questions and you would like to get to know more about this topic and how can you use the Crystal16, please contact us at info@crystallizationsystems.com or directly to Jyoti. You can write an email. You have here also her email address, jyoti.yadav@technobis.com, and we will be able and happy to actually answer all your questions or provide you with additional information. Oh, sorry, I went the other way around. A little bit about Jyoti. Jyoti is our application specialist working with us for a few years now with a PhD in chemistry applied to crystallization. And you'll hear more about this webinar from her. I pass it over to you, Jyoti.
Thank you, Carmen, for the introduction. Hello, everyone. I am Jyoti, application specialist from Technobis, and today in this webinar I will give the training on how to determine the nucleation kinetics from induction time measurement using the Crystal16 version 3 instrument. Although these experiments can be performed with the Crystal16 V1 and V2, but for the automatic analysis of the results you will need the Crystal16 V3 version software. So for the training, first we will go through the fundamentals of nucleation, which will include what is nucleation and different types of nucleation, then different methods that can be used to determine the nucleation experimentally. Then we will look into the basics of classical nucleation theory and what equations are used for classical nucleation theory. Then we will go to the software, the Crystallization Systems Software, and we will learn how to prepare the samples and how to set up an experiment for induction time measurement and how to analyze the results. We will also discuss some additional features like feedback control and multi-analysis. These features help to perform the experiment and for the analysis of the experiment more efficiently. And of course, in the end, we will have a question and answers. If you have any questions, please write in the chat box. To nucleation, what is nucleation? So nucleation is the first step of crystallization where phase transition occurs from supersaturated liquid phase to solid phase. And it has significant influence on the next phase, which is growth phase, and subsequently on the final crystal attributes like polymorph, crystal size, crystal shape, and particle size distribution. Therefore, to control these parameters, we need to control the nucleation. And to control the nucleation, first we need to measure and monitor the nucleation rate and nucleation kinetics. What are different types of nucleation? Nucleation can be categorized into primary nucleation and secondary nucleation. Primary nucleation is formation of crystals or nucleus in the absence of its own kind of crystals, and it can be further categorized into homogeneous nucleation and heterogeneous nucleation. So homogeneous nucleation is formation of nucleus spontaneously in a supersaturated solution without the presence of any foreign particles, whereas heterogeneous nucleation is formation of crystals on pre-existing surface, which can be provided by any impurity, reactor surface, or stirrer surface. Then secondary nucleation is formation of crystals in the presence of its own kind of crystals, and there are various reasons for that. For example, collision, which can occur between crystals and impeller or crystal or crystal. Then fluid shear, or we can provide external seeds, which can result in secondary nucleation known as seeding. Coming to the different nucleation theories, nucleation is a stochastic process. Therefore, it is difficult to know the actual mechanism for nucleation, but there are these two theories which try to explain the mechanism for nucleation. First is the classical nucleation theory, and second is non-classical nucleation theory. So according to the classical nucleation theory, the nucleation happens only in one step, whereas for the non-classical nucleation theory, the nucleation takes place in two or more steps, separated by an energy barrier. So here we use classical nucleation theory to determine the nucleation kinetics. So according to classical nucleation theory, the nucleation behavior of a solute in a particular solvent originates from the energy barrier for nucleation. And when the molecules combine, they form the cluster. And if the size of the cluster is more than the critical radius, this critical radius, it forms a nucleus. Otherwise, it dissolves again. Then classical nucleation theory represents the nucleation rate according to this equation, which depends upon the supersaturation ratio S, and A is the kinetic factor, which is represented by this equation, and it represents the number of active sites available to start the nucleation. Then B is a thermodynamic factor, which represents the minimum energy required to start a nucleation. Then how we can measure the nucleation kinetics experimentally? So there are two methods. First is the polythermal method, and second is the isothermal method. According to the polythermal method, which relates the metastable zone width with the cooling rate. So for this method, you determine the metastable zone width at different cooling rates. Then using different models and equations, you can determine the nucleation kinetics or nucleation parameters. Second is the isothermal method, which relates the induction time with a supersaturation ratio. And Crystal16 uses this method to determine the nucleation kinetics. So to determine the nucleation kinetics using the isothermal method, first more than 80 times induction time is measured. So these are the number of experiments performed, and these are the corresponding induction time measured in each experiment. Then the probability to form the nucleus is represented by Poisson's equation, this equation, where P is the probability and N is the number of nucleus. And J is the nucleation rate, V is the volume, and Tj is the induction time. Then the probability to form one or more nucleus can be written as 1 minus probability to form 0 nucleus. And if we substitute 0 in this equation here, we get this equation where Tj is the induction time represented by T minus Tg. So Tg is the growth time, which is the time taken by a crystal to reach a detectable size that it can be detected by the instrument or any other method. So we minus this from the measured induction time. And if we substitute these values in this equation, we get this as the final equation. Then experimentally, probability is calculated using this formula where Nt is the number of measurements in the time frame T, and N is the total number of measurements. For example, here, if we have done 93 experiments, if I see these are 93 experiments, so N is the total number of experiments, 93, and M will be corresponding to what probability we are calculating. For example, if we are calculating probability corresponding to 10 induction time, the number of time, the induction time was less than 10 minutes. For example, if it is 25, so 25 upon 93 will give me the probability for the time frame 10 minutes. So similarly, the instrument calculates the probability for each time frame and it plots or fits this equation. And this everything is only for one supersaturation. And if we repeat this for at least 4 supersaturation, we get 4 different equations, or we can perform at more than 4 supersaturation as well. And from these, by fitting this equation, we get the value of nucleation rate J and the growth time Tg. And then using classical nucleation theory and rearranging this equation, we can plot in terms of a linear plot, y is equals to mx plus c. And from the intercept and the slope, we get the values of A and the B. So for a particular solute in a particular solvent, we get a nucleation rate, which is dependent upon the supersaturation, and we get the values of A, the kinetic factor, and B, the thermodynamic factor, which are fixed for particular compound or solute in a particular solvent. Then the next question that can come up is, why do we need to perform the experiments at least 80 times? This is a study done by Zio et al., where they studied that or explained that as nucleation is a stochastic process, therefore, to control the uncertainty related to the nucleation measurement, experiments needs to be performed at least 80 times to estimate the nucleation rate or nucleation kinetics correctly with the statistics. Coming to the experimental section, before going to the software, I will tell you how to prepare the samples for induction time measurement. We prepare 4 samples of different supersaturations, and these supersaturation can be any values. And to calculate these supersaturations, we use this formula, which is C upon C star. So C is the concentrations that you want to prepare or you want to know, and C star is actually the solubility at the temperature where you want to keep your temperature constant. For example, if you want to keep your temperature constant at 20 degrees Celsius, so this C star is the solubility corresponding to the 20 degrees Celsius. Then C1, C2, C3, C4, these are different concentration that you want to prepare using this formula for different supersaturations. You can know either the supersaturation or the concentration that you want to prepare, and you can calculate the other parameter using this formula. Now I will go to the software. I will stop sharing the presentation, and I will share the screen again for the software. I hope you can see my screen with the software.
Yes.
Okay. So now to starting an experiment, now this software is not connected to the instrument. When it is connected, you will see the different reactors here, 16 reactors here, and the green line here. To start a new Crystal16 experiment, we will click on this and then put the normal information like nucleation experiment, username or description if you want to put some information here. Then we can enable this feedback control, but at first I will do without feedback control, and then I will show you with the feedback control what is the difference for the feedback. Then select the type of cap, which is basic cap, and fill the information, the compound, the solvent, the concentration. For now, I am putting some approximate values, but you can put your exact concentration and exact supersaturation. For the induction time measurement, it is important to put your supersaturation values here. Then I select my bottom storing and copy to all, and then change the values. Whatever the concentrations that you have prepared. Then after putting all the details of the 4 vials, we go to the next to program. And here we will program our experiment. First, we increase the temperature to dissolve everything. It can be anything where we know everything will dissolve. We can go at slow or high heating rate. The stirring approximately 800 RPM. Then we can maintain at the same temperature for maybe 10 minutes to know or to be sure that everything is dissolved. And to make it sure, we can add a prompt step as well. to check samples. And then we put a tune. So tune again is important to measure your induction time accurately. Then the important thing comes that we decrease the temperature at a very fast cooling rate. We decrease to the temperature where we want to keep it isothermal or constant, for example, 20 degrees Celsius. Now for the heating rate, we want to go as fast as possible. So we put 20 degrees Celsius per minute. It will calculate the duration automatically. And then we keep at this temperature for a long duration. We can keep it for 5 hours, 2 hours, 1 hour, 10 hours. It depends upon how fast it nucleates. But if you're not sure, you can maybe put for 5 hours. And then we increase again to same temperature, 60 degrees Celsius, whatever heating rate you want to put, the stirring, and maintain there for maybe 10 minutes. Now this step, we have to repeat it 80 times. So we keep it increasing, or you can directly put it 80 here. So you'll see that it is programmed for 80 times here. Although you can also perform in small numbers like 10 or 20, and then you can combine in the multi-analysis, which I will show you later. But these experiments need to be performed at least 80 times. After programming your experiment, we go to run and results, and then we select the reactor where you have kept your samples, and we can start the experiment. For now, maybe I can show you how it will affect if we use the feedback control. For example, for the same experiment, if I switch on or enable the feedback control option, we get some extra options here. So this is the target reached after, and target here is the transmissivity reached after how many more, for example, 6, and what are the units. We select the units here, seconds or sampling interval. Usually both are same, so maybe for 6 seconds. And where do you want to trigger this target? For all the whiles, or the first while where it is achieved, or you can select the specific while where you want to trigger this transmissivity. So for now, we are using all the whiles. I can select all, and these information are the same. And then I go to program. When I have selected the feedback control, I get some extra tiles here, which I see it here. So for these, instead of these, we can use these tiles. And what is the purpose? For example, specifically here, we are maintaining this step for 5 hours. But instead, if I use, instead of this, I use a feedback control here, and put these information like feedback control action. Is the transmissivity going up or down? It is going down because we are decreasing the temperature here. And what is my target transmissivity? I will say 0. And the duration, same, I can maintain for 5 hours. But what is the advantage of using this feedback control here? I will show you in the results. So if I open this experiment, which was run with the feedback control, so this is this kind of a same experiment where this was planned for 5 hours. If you see the duration here, 5 hours. But if I see in the results, this step was performed for 90 minutes only, because when the transmissivity was obtained 0 for all the four whiles, it automatically went to the next step without waiting it for 5 hours. So this is very useful for the nucleation or induction time measurements, because you are not sure how much time it will take to start the nucleation. So therefore, you can maintain this constant temperature for 5 hours or 10 hours, but it will automatically go to the next step when the target transmissivity is reached. Now I go to see how to analyze the results. I will open one experiment which was already performed. This, if I show you the details, this is for ascorbic acid in water, different concentration, different supersaturations, and it was like performed increasing, decreasing, maintaining for a long time. And if I go to run and results, I get my results like this. I can zoom in from here and see exactly how the induction time are measured. So if I see this step increasing the temperature, maintaining at the same time, and sharply decreasing and then maintaining at the same time, I get my induction times here, and it depends upon the supersaturation. For the while one, the supersaturation was less, so it took long time to start the nucleation. And similarly, with the increase in the supersaturation, it took less time to start the nucleation. And if I go to analyze here and the transition points here, I will see my induction time measurements. For example, if I go to while one, I see my induction time measurements here. If I zoom in, this is my induction time. If I see from here, starting from this green sign to the way here where it starts the nucleation, which is represented by this cloud point. And this duration is given in the table below. This is 2 hours and 28 minutes. And similarly, for each measurements, you will see the induction time here. So when this induction time will come, you must already be aware of these transition point settings. But the important or additional information for the induction time is that this is the minimum induction time, which or the minimum rate which needs to be put. Then only it will measure the induction time. That means we have used 20 degrees Celsius per minute. So this value should be more than this 15. So if we use 10 degrees Celsius per minute, then it will not determine the induction time. So to determine the induction time, the cooling rate we are using should be more than this minimum value. So this is the minimum ramp rate of the target temperature that must be reached in order to find a valid induction time. And this value is how much second it needs to maintain the same transmissivity to detect the induction time. So after going through each while, if I zoom out here, we can go through the each while and check our induction time. And the induction time in these cloud points, if you think it is not correct, you can move it, or you can add more induction time or delete induction time as you need. After going through each while, we go to the nucleation analysis here, and we see the results here. So the nucleation analysis results are represented in 4 different parts. First is the probability plot, then there is the induction probability table, the nucleation rate fitting, and the nucleation rate table. Maybe I can minimize this and focus first on probability curves. So these are the probability curves. So because the number of points are here are less, so you see a more scattering of the data. And these curves are fitted with these equations. If you see here, these are the fitted equation. And from these fitted equation, it calculates, the instrument automatically calculates the nucleation rate G and the growth time TJ, and also gives the fitting of how good the fit is. Other things you can do is you can export the image from here, or also you can export in Excel by this using this button. So these are the equations for different supersaturations. Then, and also you can change the color if you want to do, and there are options to, for the function, you can use different functions, but usually we use nonlinear least square method. Then we go down here, which is the nucleation rate fitting and the nucleation rate table. So using the classical nucleation theory, it plots a linear curve, and from the slope and the intercept, the software determines the nucleation parameters, A, the kinetic parameter, B, and the thermodynamic parameter. So this is for specific compound and specific solvent. Of course, you can change the color from here. And this is the nucleation rate equation, which is dependent upon the supersaturation. And these are the parameters. Now here, for these experiments, we have seen the data number of experiments done were not 80. So if you have done experiments in a number of different experiments, you can combine in the multi-analysis. So if I go to multi-analysis here I can start a new multi-analysis. If I click on new multi-analysis, you can put the information here, just the analysis name, some description, username, comment, and then you can add different number of experiments. Whatever experiments you want to add, you can add all the experiments, and then you can do the same analysis. Maybe I can show I already have run this experiment open in multi-analysis. If I open this and go to details, so these are the number of experiments that I have added, or I can delete as well. You can select and delete this experiment, or you can add more experiments as well. And then go to the analysis. Here you get all the same kind of information, all the four graphs here. But here you see the number of data points are more. If I concentrate on this graph, so here you see the number of data points are more than 80, so it's a better fit here. And for each supersaturation, you get the information here, the color, different supersaturation it represents. You can change the color from here, like this. And also you can export this table as well in Excel by right-clicking and exporting. And this, from this table, then we get the another information of the classical nucleation theory. And similarly, from the classical nucleation theory, we get the same parameter A and B from here. So here the fit of the curve is better because the number of experiments we have combined here are more than 80. So I think this is the benefit of using the software where you don't have to do the calculations, any calculations manually, but you get all these calculations automatically while you are even doing the experiments. I think this was all for in terms of the software. I think I have explained more. Of course, if you have any questions, you can ask. I will stop sharing this software and I will again share my presentation. And I will just do you see my screen?
No, I see you still. You need to share the other screen.
Sure. Okay.
Yes. Yes.
Okay. So thank you all for joining. If you have any questions, we are happy to answer.
Yes. So thank you very much for joining us today. Jyoti has shared with you a bit of background information about kinetics and induction time measurements and nucleation. Also, how you should prepare your samples and also how to use the software of the Crystal16, how to export your data and how to see the data actually to analyze it. If you have any other further questions, please do not hesitate to contact us at info@crystallizationsystems.com or just via our website or directly to jyoti.yadav@technobiz.com, and we will be happy to share with you the information. Tomorrow you will receive, as mentioned at the beginning, an email with the recording of the place, a link where you can rewatch the recording. If questions come up, please let us know. We'll be happy to help you. I think this was our last webinar for this year. Thank you very much all for joining us today. And during this year, during our webinars, we will start next year in January with another webinar. End of January. Do we have a date, Irina? 30th of January. It's our next webinar. Until then, US, happy Thanksgiving, and everyone, happy winter holidays, and see you next year. Bye.